So the title of the talk today is Exercise and Fatigue, and this is a picture actually of Rich Beloff from his undergraduate days, being a research subject. We've been studying fatigue for a long time. For those of you who have some familiarity with exercise physiology, the Harvard Fatigue Lab, for example, started in the late 1920s to the 30s, and then through World War II. You may recognize some of the names there. Henderson of the Henderson-Hasselbalch equation was one of the key players in setting up the Harvard Fatigue Lab, and D.B. Dill. And I don't know if this picture is taken from the Harvard Fatigue Lab, but in some ways this is a little bit disturbing to me because other than the lack of computer technology, this is still fundamentally a lot of the type of stuff that we do today. So I'm not sure our field has progressed that much. But fatigue is certainly an important part of our everyday existence, and of course, this being football season, the great Vince Lombardi is believed to have said, anyway, fatigue makes cowards of us all. I'm not sure if that's actually true that he said that, but I think there's some truth to that. Certainly in the game of football, if you can win in the fourth quarter because you pound your opponent into oblivion, that's an advantage. But one of the problems with looking at fatigue is that we kind of use the word fatigue to define a lot of different things. We don't always mean the same thing, and people talk past each other a lot when you study fatigue. So this is the definition that I think most exercise-type people will roll with. Any exercise-induced reduction in basically the ability of the system to produce force and or power. But of course, we have fatigue used in a different context. I think the everyday usage of fatigue is a little bit different than that. And certainly in clinical settings, when you have chronic fatigue syndrome, fibromyalgia issues, and stuff like that, the idea of fatigue is a little bit different than what we would talk about from a straight muscle performance or exercise performance perspective. And so this is a picture of me, actually, before my low-carb diet, for those of you who are wondering. As I said before, I think we talk past each other a lot when we talk about fatigue. So there's a lot of ideas that float around when we discuss fatigue. We certainly measure performance somehow. I think pacing is an interesting area that's getting a lot more study. And how is it that we pace ourselves, and what is the neurobiology of pacing? We use the term endurance, exhaustion, dyspnea, shortness of breath. And you can read down the rest of the list here. I think actually the word asthenia, I'm sure this will never happen. This is a term that I first heard a few years ago at a conference in Colorado, and it was used by a physician from Spain who actually does a lot of exercise work, including work with elite athletes. But his area of interest now is actually looking at exercise in cancer. And the fatigue in that context, the psychological inertia that one has to overcome in order to engage in physical activity is certainly not a trivial consequence of a variety of disease states, but it's a little bit different than what we talk about typically in exercise physiology. So I think sometimes if we could introduce a term like asthenia or something like this to help differentiate what we're talking about, I think our work would be a little bit easier to wade through. I think it's also helpful to picture fatigue as a protective mechanism, that one might imagine that evolution has created a series of mechanisms to prevent you from exercising to an extent that would cause you harm. And there are possibilities of perhaps of you overcoming those governors, if you will, but you might recognize this is a picture, a screenshot I captured from YouTube. I don't know if that's a copyright violation, but from the 1984 Olympics in Los Angeles. So this Gabriela Anderson Schleif, I'm not sure I'm pronouncing her last name correctly, but one of the iconic images of the 84 Olympics, that was the first women's marathon in the Olympic Games, was her last lap around the Los Angeles Coliseum. And she was clearly in a state of heat exhaustion, but arguably was not in heat stroke. The medical staff, apparently, as I did a little reading on this, determined that she was still sweating. So they let her continue that last lap. And that was actually a controversial move on their part. But ideally, we have mechanisms to prevent us from routinely being able to exercise to an extent that we are in a life-threatening situation, can cause permanent damage. So where might fatigue be affecting, what mechanisms are going to be in place to cause us to fatigue? And so typically we typically think of fatigue as being either of essential origin and or a peripheral origin. And I put the neuromuscular junction in here just for completeness, but it looks like under in vivo conditions, if you get an action potential on an alpha motor neuron, you're going to get enough acetylcholine to cause the muscle to reach threshold on the other side. And I'm going to go this a little bit backwards. We'll talk about some central stuff towards the end, but right now we'll focus more on what's happening at the level of the skeletal muscle. And a few dominant ideas of what's going on. And I would suggest to you that, in fact, a lot of these things are probably going on, depending upon the type of task we're talking about. So one thing that might be happening is that you run out of stuff. So you can run out of creatine phosphate, and in fact, that happens under very high-intensity conditions. In theory, you might be able to run out of adenosine triphosphate. We'll talk about that. The system seems to very intensely protect you from getting ATP depletion and glycogen depletion. And this can happen with certain types of exercise if the intensity is high enough and the duration of the exercise is long enough. The flip side of that is what if stuff builds up in skeletal muscle? So lactate or lactic acid, we'll talk about that in a little bit. Hydrogen ions, so pH clearly falls when you engage in high-intensity exercise. And then PI here stands for inorganic phosphate, and we'll talk about that here in a little bit, and ammonia, which I'm not going to address. But there's other things that possibly could accumulate in skeletal muscle that would interfere basically with actin-myosin interaction, ability of the contractile proteins to generate force. But I think most of what people are focusing on now, at least at the level of skeletal muscle, is problems with what is referred to as excitation-contraction coupling, basically getting the signal from the muscle cell membrane, the action potential on the muscle cell membrane, to calcium release and calcium binding to troponin at the level of the skeletal muscle. So we'll talk a little bit about that later on. And I put this slide in here because I think there's a lot of money being made out there in different sort of nutritional and to a lesser extent pharmacological interventions that try and target fatigue. And also the stuff that works probably gives us some insight into the mechanisms of fatigue. So this is just a laundry list here. But there's a lot of literature out there looking at the influence of caffeine, both at the level of isolated animal muscle preparations as well as in human and animal consumption. This NAC here, I don't want to try and pronounce that. This was only introduced to me a few years ago by a symposium at the American College of Sports Medicine meeting. There's a group in the University of Kentucky, actually, that's been looking at this pharmacological antioxidant, and at least in isolated preparations, seems to have some efficacy in limiting force loss with repeated contractions. Ways of buffering pH change. And so sodium bicarbonate ingestion has been around for a long time. Sodium bicarbonate ingestion works. It will increase blood pH. It'll alkalize the system. The problem with sodium bicarbonate is that only half the people can take it without throwing up in terms of the doses that you have to get in order to cause a significant pH change. But this beta-alanine, if I get my mouse back here, beta-alanine as part of the carnosine system. I'm not going to talk about that in any detail, but this is in a nutritional supplement that's been on the market for a couple of years now. And there's actually a lot of good data showing that it is a pretty good pH buffer, and it is quite effective in attenuating fatigue response in certain types of exercise models here. Creatine supplementation has been around for a long time. I'll have a few slides on that. A few of these others I'm not going to talk much about. I just want to mention here briefly, of course, this is illegal, but certainly in the sport of cycling, erythropoietin, and in the old days, blood doping, where you'd actually infuse back red blood cells. And that actually, I think, first came to light in the '84 Olympics also, when cycling was introduced, certain cycling events were introduced in the Olympics, and blood doping was not illegal, and people talked about it relatively openly. And it does seem to work. All right. I'm not a biochemist, so I don't want to take a whole lot of time here talking about biochemistry, but this is certainly, at the level of skeletal muscle, the fundamental reaction that we're primarily interested in. So we have adenosine triphosphate, and we need to pop off that terminal phosphate group here in order to release energy. In terms of buffering ATP changes at the level of skeletal muscle, though, we have creatine phosphate floating around, and we can donate the phosphate from creatine phosphate back to ADP, giving us ATP again. And so this is the fundamental reason why creatine supplementation is used. If you can, in theory, increase your free creatine levels, also increase your creatine phosphate stores in skeletal muscle, you can engage in this process a little bit longer. And so that might give you a performance advantage. This, I think, certainly don't memorize the numbers here, but I think we as exercise physiologists, people in my discipline, and we don't really kind of appreciate this enough. We have a lot more creatine phosphate in skeletal muscle than we do ATP. Creatine phosphate is a very important player in energy buffering and also actually getting energy in the form of ATP from the inside of the mitochondria and out to the contractile proteins where it's being used. So given these numbers here, if you are engaged in maximal exercise, you will burn all of, if we didn't have creatine phosphate, you would run out of ATP in about 1.5 seconds. So even in maximal bouts of exercise, like the 100-meter dash, Usain Bolt does it somewhere between 9 and 10 seconds. He's depending very heavily on the creatine phosphate system to provide him with continual levels of ATP in order for him to break those records. All right. So creatine supplementation, a lot of money being made out there. This has been around probably since the mid-90s. It's starting to become commoditized now. I don't think vendors make as much money as they used to, like in the old days. But the idea, once again, is we can increase creatine concentrations and creatine phosphate concentrations in skeletal muscle. It's like adding charge to the battery. And I will just say parenthetically that there's a lot of work looking at creatine supplementation as a neuroprotective agent. That if you can increase creatine phosphate stores in neurons, certainly in animal models, you can see that you minimize the extent of neuronal damage in experimental models of stroke and experimental models of traumatic brain injury. And there's also some interesting stuff looking at things like Huntington's disease and so on in animal models. Unfortunately, it doesn't seem to work that well in humans. But the idea is if we can increase our creatine phosphate levels in skeletal muscle, we can work a little bit harder maybe in training, and certainly if we're involved in a sprint performance or something like that, performance will be increased. And in fact, this is one of the early studies that showed the beneficial effects of creatine supplementation with, this was sprint cycling. I believe this was 30-second Wingate test, for those of you who might be familiar with that. But just pedal as hard as you can for 30 seconds. For those of you who've done it, it's a remarkably unpleasant experience. But it's kind of a standard undergraduate exercise task in an exercise physiology course. What you can see here is that after creatine supplementation, non-trivial increases in the amount of work that we performed in those cycling bouts. And lots of studies have showed basically the similar thing, similar process since then. Here's my very shorthand version of glycolysis here, because we're going to talk about lactic acid and lactate here in a bit. So if you're using carbohydrate as a fuel source during exercise, well, of course, we can get that from the blood. We can break it down directly from skeletal muscle. And the idea is that we can get the glycolytic pathway to go very rapidly. We get lots of ATP. Well, we get a little bit of ATP, but if we do this fast enough, we get a lot of ATP. And depending on the exercise conditions, maybe we'll produce lactate, or maybe most of that will be converted to left as pyruvate and then sent into the mitochondria and into the Krebs cycle. And so here is a summary of that. Pyruvate again at the top, ATP here at the bottom, Krebs cycle electron transport system. This was sent to me by a friend of mine at the University of North Carolina. I assume this was from the UNC campus. So I thought that was cute anyway, if nothing else. This might bring back bad memories for lots of us who had to memorize this, of course, on multiple occasions as undergrads and maybe in grad school. But that leads me to talk about lactate or lactic acid a little bit here. And certainly, my experience going through high school PE and so on, I think a lot of people still hang on to this. Well, the reason that you're fatiguing is because a buildup of lactic acid. So I'm going to take several slides and talk about problems with lactate. There's nothing special about this study here, but this was a simulated soccer game from a lab in Scandinavia somewhere. And these were sort of like junior elite soccer players. And they took periodic blood samples during the simulated game. So here's the first half of the game over here, second half of the game over here. There's a couple things I want you to notice. One is the lactate numbers are all over the place. There's a great deal of variability. Now, I don't think they included the goalie here. But there's a great deal of variability in the lactate response to a soccer game. The other thing is, in the second half, lactate levels are lower than they are in the first half. You'd think if you're tired and lactate was causing fatigue, lactate levels would be high when you're performing less well. But in fact, lactate levels are lower in the second half of the simulated soccer game. This is data from the same study. This is comparing muscle lactate. So they did periodic biopsies. Volunteer for that study, right? Muscle biopsies. And blood lactate levels over here. And what you see is that the muscle and blood lactate numbers their data are very poorly correlated with each other. What's going on inside the skeletal muscle is much different than what you see out there in the easy-to-measure blood lactate levels. Lactate, there's a whole complex series of transporter molecules that are required for you to get lactate from the muscle into the blood. And it's really the muscle levels, muscle pH and muscle lactate levels that we would be primarily interested in. And the blood lactate doesn't really probably tell us a very accurate picture of what's going on. I always tread lightly when I talk about this stuff because I'm not a biochemist, but there's a paper that came out from Rob Robergs when he was at University of New Mexico. And it was a big review in American Journal of Physiology, fairly controversial, a lot of letters to the editor going back and forth. But his argument, and I think it's a correct one, is that if you look at the actual biochemistry of glycolysis, all of these glycolytic intermediates are deprotonated all the way through. The pKa levels here are in the 2s and the 3s, which means that we don't produce pyruvic acid and then convert that to lactic acid. We produce pyruvate and convert that to lactate. So the model that I think a lot of people have in their heads, we produce lactic acid, that's an acid, so we donate that proton, that's what causes the acidity. You clearly become acidic when we exercise, but it's not from the deprotonation of lactic acid to lactate. Now, why we become acidic is actually people are still arguing about that. So perhaps this is just a semantic argument, but we don't produce lactic acid at physiologic levels. We produce lactate. We do become acidic. And there's this whole argument here in the exercise biochemistry world, and I'm not going to get into that, about why we become acidic. But it's not because of lactic acid production per se. And in fact, lactate is arguably a very important molecule. It's a fuel substrate that is used during exercise. But what about acidity? Ignoring the lactate issue per se. What about acidity? And decreases in pH, certainly at the level of skeletal muscle, people have been for a long time hanging their hat on that. The reason that performance goes down is you become acidic. And accumulation of hydrogen ions does all sorts of stuff with calcium dysregulation and interfering with cross-bridge formation and stuff like that. But about 10 years ago, what people started to look at was a lot of this old data examining the relationship between pH and fatigue. And what they noticed was that all these studies looking at the effect of pH on muscle performance in isolated animal preparations anyway was done at room temperature. And so they started redoing a bunch of these experiments at physiologic temperatures. And what you see is that at physiologic temperatures, the effect of pH change on muscle performance is quite modest. And you have to get pH changes down like 6.4, 6.3 inside skeletal muscle before pH starts to really seem to be a major player in terms of affecting muscle performance. So pH isn't unimportant, but it's probably less important as a fatigue agent than we probably thought it was, say, 10, 15 years ago. Some other potential fatigue agents, so accumulating things in skeletal muscle. And I'll focus here next on inorganic phosphate. So remember, when we need energy, we take ATP, pop off that terminal phosphate group, releases energy. Now we get ADP and that inorganic phosphate floating around. Ooh, I'm a couple slides ahead of myself. Let me hammer lactate a couple more slides before I move on. This is a study looking at, in this graph here, this is rating of perceived exertion. So some of you may be familiar with the typical Borg scale. 6 would be relatively easy, 20 would be maximal. So this is how hard are you working? They give you a number. 20 would be I'm working as hard as I possibly can. And so these subjects were pedaling for an hour on a cycle ergometer at a load about 2/3 of VO2 max, 2/3 of their maximal oxygen consumption. And what you see is as they went through the exercise bout, sure enough, RPE went up. So here, O stands for overall, leg here, L stands for leg, and O stands for chest. How hard does it feel at these different levels? So all of these basically follow the same general trend. They're pedaling at the same power output for an hour. It's getting harder progressively. And also, heart rates are continually going up. Now, keep in mind the power output's the same, and so I always like to point this out, the phenomenon of cardiovascular drift that I think we underappreciate when we talk about exercise. If you exercise at a fixed power output, your heart rate, if you're looking at heart rate zones and stuff like that, your heart rate will drift up over time. But anyway, we have cardiovascular drift going on as we would expect. But what you see here is the lactate levels, in fact, are going down over the last 2/3 of the exercise bout. Exercise getting harder, heart rates are going up, lactate levels are going down. So there's some dissociation there. So bottom line here, interpret lactate with caution. I won't go over these measurement issues here, but there are different issues in terms of how we get these lactate numbers. And I alluded to this earlier, but depending on the type of sport, if you're talking about athletes here, one of the goals of your training is to try and make these athletes generate very high levels of lactate. The point is to train the glycolytic pathway to be turned on a lot. We want you to produce lots of lactate. And lactate is a fuel substrate. So don't blame lactic acid. I think it's gotten an unfair rap over a long period of time. So let me go to this slide right here. So inorganic phosphate. And this seems to be the one metabolite that has certainly gained a lot of attention the last 10 years or so. So inorganic phosphate is being represented here by this purple sphere. And what's going on in skeletal muscle? So here we have contractile proteins. Here's the T-tubule, and SR here stands for the sarcoplasmic reticulum. So we store calcium in the sarcoplasmic reticulum, and we tell the muscle to contract. That information, the action potential, causes calcium release. Calcium then is the trigger to cause the contractile proteins to interact with each other. Calcium binds to troponin and so on. But what seems to be going on with inorganic phosphate is as you exercise and ADP levels go up and inorganic phosphate levels go up, inorganic phosphate does a couple things. One is it interferes with calcium movement across the sarcoplasmic reticulum. So it can interfere with calcium pumping, so muscle relaxation after a contraction is slowed. And it also tends to bind to calcium inside the sarcoplasmic reticulum. So it appears to form a precipitate inside the sarcoplasmic reticulum. So now you have less calcium that's available to be released into the sarcoplasm of the skeletal muscle. Basically, the more calcium you have, the more force you're going to get. So now if we're preventing calcium from being released from the sarcoplasmic reticulum due to the accumulation of inorganic phosphate, we're going to suppress the ability of that cell to generate force and generate power. This is an isolated animal study. So they took a muscle preparation, and here they're looking at the effects of caffeine. Now, I should point out that these are caffeine doses here that would kill you if you took them. Okay, so caffeine used by humans, 100 milligrams in a cup of coffee, 200 milligrams, something like that, that is not the level we're talking about here. And in fact, typically the caffeine that you take, the effect seems to be a little bit more in terms of autonomic nervous system function and binding to adenosine receptors in the central nervous system. But caffeine is used in muscle physiology to study fatigue, among other things. So this is repeated trains of muscle contraction. So they electrically stimulate this muscle, and you do this long enough, all of a sudden the muscle starts to fail. And these graphs down here are the calcium responses. And what they do is they blast the system with caffeine here right at the end. So now they blast the system with caffeine. Caffeine stimulates calcium release from the sarcoplasmic reticulum. This is fairly strong evidence that, at least at the level of the skeletal muscle, it's calcium regulation that's the main player. We can basically, even though we've done this whole fatiguing bout here, if we blast the system with caffeine and force calcium to be dumped out of the sarcoplasmic reticulum, we can get force levels that are about where we started with that muscle. So pretty strong evidence that it's really calcium regulation at the level of skeletal muscle that's affecting muscle performance with fatigue. All right. Is fatigue all in your head? After I just give you this whole spiel on what's going on at the level of skeletal muscle. This is a review I wrote, it came out 5 years ago now, in response to a series of papers that were published in British Journal of Sports Medicine by Tim Noakes, who's a relatively prominent, he's a physician actually, but an exercise researcher in University of Cape Town in South Africa. He's an interesting guy. I've never chatted with him. He's very well published, does a lot of interesting work. I think my take on Dr. Noakes is that his data is more interesting than his interpretation. He does these studies, and I look at the data, that's really good data, but then I think he screws up the discussion section. Nonetheless, Tim Noakes' bit is that all fatigue is really a fundamental process going on in the central nervous system, and that what's going on the level of skeletal muscle is largely irrelevant. So he has some interesting points, but I think there were some weaknesses, and we're not going to go through all of this, but this model is out there. If you Google central governor model, you'll get some interesting stuff out here. But this is a quote from one of his BJSM reviews. So fatigue should no longer be considered a physical event, but rather a sensation or emotion separate from an overt physical manifestation, for example, the reduction of force output by the active muscle. And so all the stuff we've been talking about in his model only serves as a source of feedback to the central nervous system. So the contractile performance per se is not the cause of fatigue or the regulator of performance. And I thought this was a very illuminating quote here from an earlier review he did. And he said this several times, at least in the early 2000s. The most interesting question in exercise physiology, why do muscles not go into rigor when they engage in high-intensity exercise? So why don't they go into rigor? Well, the central governor model would suggest that the CNS prevents you from doing that. And I think there's some truth in that. So the CNS regulates motor unit recruitment, basically the activation of muscle, to an extent that it prevents you from working the muscle to the extent that it will go into rigor. And I should point out, I didn't make this idea up, it's down-regulation theory. I think you can go back to the 1970s and people talking about this idea of preventing ATP depletion at the level of skeletal muscle. Fatigue is a protective mechanism to prevent rigor or catastrophe, or however you want to pronounce that, or however you want to describe that. And there's nothing particularly special about this study, but I think it does illustrate kind of a weakness in Noakes' argument here, data that he'd ignored. So this is, once again, isolated animal preparation. So they take animal muscle, they electrically stimulate it over time, and here's the force curve here. And here's another measure of performance, but we'll focus on force here. So we keep stimulating this muscle, sure enough, performance declines and reaches some low level down here. With NMR, you can look at things like creatine phosphate concentrations, ATP concentrations, and inorganic phosphate concentrations. So what do you see? This is the time period here during the fatiguing exercise bout. So when this was going on over here, we're looking at this period right here. So here we are at rest. We start fatiguing the muscle electrically. Creatine phosphate levels decrease dramatically. Inorganic phosphate levels increase dramatically. ATP levels hardly change at all. Pretty stable. And this is a fairly common observation. You will see that different techniques will show, ATP levels will go down a little bit. But at the level of the skeletal muscle, the system aggressively defends ATP concentrations. You don't need the CNS to do that. Fatigue at the level of skeletal muscle prevents, or at least inhibits you from exercising the muscle to a state that would cause rigor. And I started looking through some of these old studies where they would electrically stimulate muscles. It's really hard to induce a rigor state in a skeletal muscle with electrical stimulation. Just doesn't want to happen. You have to blast it for a long period of time, and maybe you can get a little bit of evidence of rigor showing up. So at the level of the skeletal muscle, these protective mechanisms exist. You don't need the CNS. I haven't actually defended this with anything I've covered with you yet, but the more I look at the central governor model stuff, it's interesting. What I think as we start talking past each other, what Noakes is really talking about is pacing. He's an endurance athlete, and that's kind of the thought process that led him down to this idea of the central governor model. How do people pace themselves? When you run a 10-kilometer race, you don't sprint the whole thing. You're not running as fast as you can all the time during that race. Right at the end, you may kick, but pretty much the rest of that race, you're running at sub-maximal levels. Why is that? Pacing is interesting, but pacing is related to fatigue, but it's not the same thing. All right, I had to throw in a picture of my sweet motorcycle in here, but it actually does have a point. Unfortunately, this is not the tachometer from my bike. I forgot to take a picture of it, but I stole this off the internet. But what you notice about tachometers from high-performance engines is that the numbers start changing colors after a certain point here. And if you look at the technology of high-performance engines, they have rev limiters in them. By design, the engineers prevent you from revving the engine to a level that would cause engine failure, hopefully. So the engine is physically capable of revving higher. The electronics prevent you from doing that, to prevent you from damaging the engine. This is a similar type of phenomenon occurring when you exercise. And kind of like what Noakes is arguing. And I'd say that, yeah, there's probably some of this going on. This is actually data from Noakes' lab. This was another study that probably wouldn't want to volunteer for, but this was a 100-kilometer simulated race in the lab. So they bring them in the lab. I forget how long this took. But these were high-level cyclists. They do this for fun. But they did a 100-kilometer simulated trial in the lab. And then periodically what they would do is they would ask them to do a sprint. So pedal as hard as you can. Produce as much power as you can. And as they progress through here, what you see is that the performance in each of these sprints goes down as they're fatiguing during the exercise bout. And what you see here, this is electromyographic data here, this bottom graph. So they put electrodes on the skeletal muscle, measure muscle electrical activity. Generally speaking, the idea here is that the bigger the electrical signal, the more motor unit activation there is. Now, there's problems with this during fatigue. But what you see is kind of what Noakes would suggest is going on. As you fatigue, the system is inhibiting you from turning on all the skeletal muscle that you might. It's doing that to protect you from damaging yourself. And I think that's probably a reasonable interpretation, although the EMG data here is actually a little bit problematic when you use it under these types of conditions. Here's another approach, and we can do this over in the lab with both electrical stimulation and now with magnetic nerve stimulation. But here's a task where they ask a person to do a maximal isometric contraction. Just push as hard as you can. And almost from the start, once they get up to the peak here, their performance goes down. If you ask someone to do a maximal contraction, they start decreasing their performance almost immediately. And what you see here is that where each one of these arrows is, they will superimpose maximal electrical stimulation. So this is with real people. So we're putting either electrodes on the muscle belly or stimulating, if this is the thigh muscle, the femoral nerve. And so this blip here represents the little bit extra force you get from the electrical stimulation. So when we're not stimulating you, this is what you're doing voluntarily. If we shock you maximally, we in theory can turn on those last few motor units that you are not turning on voluntarily. And the magnitude of these blips here basically gives us a sense of how much the CNS is not letting you turn on skeletal muscle. So that's kind of a common theme for another approach to assessing the ability of the CNS to allow you to turn on muscle. Let me skip that slide. That's not probably that helpful, and we're running a little bit out of time here. Well, let's look at this task here. Now, this is a rather odd task. So they have to do 30 plantar flexors, 30 sets, I bet, 50 contractions per minute. So this is not a trivial task here. And basically, after you do this calf exercise, they have them do a maximal contraction. As you'd expect, force output goes down after the task. You can't produce as much force with your plantar flexors as you could. But activation didn't really change under those conditions. So under some conditions, the CNS is really not what's limiting you here. They're about 98% activated pre versus post fatigue, and yet force goes down. So what has to be going on, presumably, is something at the level of skeletal muscle. So it's not all CNS. Here's a different, I think this is actually the same lab here. This was after a 30-kilometer running race. So they tested them maximal contraction before and after. Here's the voluntary force output. And after the 30-kilometer running race, their ability to produce force from the thigh muscles decreased about 25%. And their activation did go down. So the CNS is limiting this a little bit. So it went from 99 to 91. It's not the whole story, though. So both the CNS as well as changes at the level of skeletal muscle are contributing to the decrease in performance that you see. And this is data, basically the same data, and I'll skip that a little bit here. So that leads me to this slide here, the idea of TAS dependency. So is activation limiting what you're doing? Well, it kind of depends. It depends on the fatigue model we're looking at here. And this is a little bit unsatisfactory to a lot of people. So the idea of TAS dependency is basically that what's causing fatigue depends upon what you're doing. And they think, well, we'd like, and frankly, Noakes really wanted to come up with a grand unifying theory of fatigue that included not only exercise, but also chronic fatigue syndrome, fatigue and fibromyalgia, cancer, all that sort of stuff. And I don't think it's possible. I think what's causing fatigue when you run a marathon is much different than why you missed the 5th rep of a weightlifting set and you made the first 4. These are different enough tasks that the physiology is different and what's causing fatigue is different. So TAS dependency is a phrase that I guess I hang my hat on. What's causing fatigue really depends upon the type of task that you're talking about. And it's not all lactic acid. It's not pH. It's not all inorganic phosphate. It's not all in the brain. And the interplay of those depends upon the type of task that you're looking at, as well as the subject here. So here's TAS dependency, marathon run versus a 3RM squat. Substrate depletion versus metabolite accumulation. Clearly, we can cause people to have a decrease in performance if we play with their glycogen stores. A much different mechanism than if they're glycogen loaded and so on. All right. I'm going to switch gears just a little bit here and talk about what I consider to be kind of odd but yet interesting fatigue observations. So this comes out of Roger Anoka's lab at the University of Colorado. And as a longtime Husker fan, of course, it was my duty to hate the University of Colorado. But now they're in the Pac-12, so I guess I can go ahead and present Colorado data without too much anguish. But what they did was they had people do forearm flexor fatigue tasks. But they had them do it under 2 different conditions. Now, the body position here is a little bit different, too, and that may be playing a part of this. But in this task here, this is an isometric apparatus. There's a load cell in here, and the subject looks at a computer screen. So there's a target force. And so the point is just get up that force and hold it as long as you can. This task here is set up such that the subject has to produce the same amount of force as they did up here. But now the task is not matching a force tracing on a computer screen. The task is holding a weight at the same joint angle that elicits the same force output. And do you get the same fatigue response? And the answer is no. So males and females are a little bit different here, but if it's the force task versus the position task, time to failure, now keep in mind I'm talking endurance, so it's not exactly fatigue, but presumably these are are intertwined enough. The force task allows people to maintain that level of force output longer, markedly longer, than the position task does. So something's different, presumably with how the brain is perceiving these tasks, that affects when they decide to quit. To me, that's interesting. I'm not sure what it means, but it's interesting. What about fatigue versus endurance? I just pointed out that that's really an endurance task. So this data from actually the same lab. Here they did 20% maximal voluntary isometric contraction until failure. So same idea. So just generate this force, hold it at this line as long as you can. And the force was, in this case, 20% of their maximum. And I'm going to talk about the males versus females here. So how much force could they produce at maximum before they started the task? How much force could they produce maximally, voluntarily, after they failed? So they'd fail, wait a little bit, okay, push as hard as you can. How much force could they get? So both males and females had about the same level of force decline, not exactly the same. What they found was that women were able to hold that almost twice as long as men were. So they got to the same level of fatigue, more or less. But it took women twice as long to get there. So they had better endurance properties. So I just illustrate this. The language is important now. So the fatigue was the same. The endurance was not. And language matters here. Words matter. And that's one of the reasons I think we talk past each other a lot when we look at the fatigue literature. All right. What about heat? And this is certainly in the last 5 or 6 years, this has really gotten a lot of attention. So these subjects were asked to sit. They didn't exercise. They sat for 2 hours under 3 different conditions. One is at 68 degrees. The other, 2 hours sitting at 122 degrees. And then the third one, 122 degrees, plus they had some head cooling thing. And then they look at their force output as well as their voluntary activation under these different thermal environments. So I just want you to look at the top ones here. The rest of the stuff probably a little busier than we need to focus on. What you see is just sitting in a hot environment. And my recollection is they gave them fluids. So they were not dehydrated here. But just sitting in a hot environment decreases the amount of force you can produce. And it seems to be driven by changes in voluntary activation. The CNS is not letting you turn on muscle when you're hot. And there's a lot of observations, a lot of studies showing basically the same thing. The CNS does not like you to do things when it's hot. There's a whole bunch of, this is a review paper that came out 6-7 years ago now, but decrease in voluntary activation with exercise in the heat, so exercise hyperthermia, variety of different ideas of what's going on here. But the bottom line is that when you exercise in the heat, your brain is very aggressively preventing you from doing things physically that you could do in a cooler environment. So I just want to point that out that this is another idea of this protective mechanism. And I don't remember the numbers now, but there are core temperature numbers where basically once you cross a certain number, it seems like the CNS very aggressively doesn't want you to engage in exercise. And just anecdotally, you can kind of experience that here in Iowa in the middle of summer when it's 95 degrees and 90% humidity. You walk out of your air-conditioned home and that wall of heat hits you. The last thing in the world that you want to do is go for a run, right? I mean, psychologically, you don't want to exercise. So I just point out there's a whole lot of very interesting data looking at exercise in the heat. What about carbohydrate consumption? This is a very recent review that came out. I like this. We don't have any students in here. A couple students, I guess. You're a student, right? Really? Okay, we don't have any students. Evidence-based practice. So I was going to make a nice little tie-in there with evidence-based practice. So this is a forest plot from a meta-analysis looking at the effect of carbohydrate consumption on time to exhaustion. And as typical for exercise studies, we have small n's. And so all these studies, this would be a non-significant study, right? The 95% confidence interval includes the null value here. Some are significant, some of them are not significant. But when you put them all together at the end of the meta-analysis, you see, yeah, it's not a reasonable effective carbohydrate consumption during an exercise bout, prolonging your time to exhaustion. So for whatever reason, the system likes to have carbohydrate. But it turns out you don't actually have to consume the carbohydrate to have the effect. Mouth rinsing with carbohydrate solutions, you don't swallow. These subjects spit this out. If you mouth rinse, this was a simulated time trial here. So the smaller numbers mean better performance. So how long does it take you to pedal a certain distance? And I forget what the task was here, but primarily focus on this. So the subjects either rinsed with an artificial sweetened solution and spit it out, or they rinsed with a carbohydrate solution and spit it out. But both of them, they didn't drink anything other than water. Just sensing carbohydrate, not the sweetness, but the actual glucose. That glucose sensing in the mouth seems to tell the brain that things are okay. You can pedal harder. Several studies now coming out looking at this idea of carbohydrate mouth rinsing. So it might not be the actual carbohydrates floating around in the blood. It's just the brain knowing, looks like you got carbohydrates, so things are cool. We'll keep going. And finish up here talking about leading into a study that we're doing. Dan Chambers and Julia Ronenbaum and David Strom. We're doing a study that is based upon, I must be getting word finding problems and so on, but as I get older. Based on a couple of these studies here. So one is effective acetaminophen on cycling time trial performance. This paper came out in 2010, actually. So this is a simulated time trial under conditions of acetaminophen consumption. I believe this was about 1,000 milligrams, or placebo. And what you see is that on net, some of these individual comparisons weren't statistically significant, but if you just integrate the area under these two performance curves here, what you see is that under conditions of acetaminophen consumption, these people pedaled at a higher power output than they did under placebo. So the thought here is that analgesia plays a role. And so this is the same data, same study, but here they looked at rating of perceived exertion, asking them how hard are you exercising, and then here looking at a separate level of pain. And I think it's important to differentiate exertion from pain. People are able to do that. How hard are you exercising? Give me a number. How much does it hurt? Give me a number. Those numbers are correlated, but they're not the same. But what you see is that basically both of these lines are superimposed on each other. So what acetaminophen seemed to do was allow people to exercise at a higher intensity for the same level of exertion, if that makes sense. So the rating of exertion was the same under both conditions, but it was at a higher power output when they took acetaminophen. So the thought here is that the analgesic effects of acetaminophen are boosting performance. But I want to contrast that with this study here. This came out in 1997. This was a study done in Europe using Vioxx, which you can't use anymore. But Vioxx is a cyclooxygenase 2 specific inhibitor. And in addition to the analgesic properties of most of these over-the-counter pain meds, they most often also have antipyretic effects. And so what you see here is they did a 45-minute run followed by a 45-minute bike ride. And the core temperature here is what they're measuring on this graph. So when they took Vioxx, by the time they got around to the cycling bout, their core temperature was lower when they took Vioxx. So this is fixed pace. Everyone's exercising the same intensity under both conditions. They take Vioxx, their core temperature is lower. Remember, the system doesn't like you to be hot. So your performance presumably is going to be significantly affected if your core temperature is lower. Mean body temperature, same picture here. Heart rates lower at the same exercise intensity when they were under the Vioxx condition than they were when they're taking placebo. So what I think is interesting here, a couple things are interesting, but one of it is that when your core temperature goes up when you exercise, it's not just due to the inefficiency of converting chemical energy into mechanical work. It's not just the heat given off from the inefficiency of the system. Some of this is due to a fever response. Normal exercise induces a fever response. My own little sub-idea, and other people are thinking this too, when you look at people who actually go into heat stroke, actually, interesting that Noakes has looked at some of this stuff too. If you look at the exercise conditions and how hard they were working, that is the exercise conditions, how hot it was, what the humidity was, and you look at some of these people who go into heat stroke, they shouldn't have gone into heat stroke. The heat load was not enough. There's probably what was pushing them into heat stroke was probably some fever response. Maybe they were running the race when they had a little infection going. Maybe they got some GI trouble and LPS levels start getting elevated in the blood and stuff like that. But anyway, over-the-counter analgesics like ibuprofen and like acetaminophen have antipyretic properties also, as well as the analgesic properties. So that's the study that hopefully we're starting here shortly. I've got a new metabolic cart coming up, replacing the one in the first slide. So we're waiting for the new cart to show up, and hopefully we'll get that study launched, looking at exercise fatigue responses, both with respect to looking at pain, rate of perceived exertion, as well as changes in core temperature to high-intensity work bouts, both fixed pace as well as time trials. And to sum this up, I'm a few minutes over, apologize for that. Take-home messages. I think both the central nervous system as well as the skeletal muscle itself are important players, and how important they are depends on the fatigue task you're talking about. So TAS dependency, I think, is critical. And fatigue is not your enemy, necessarily, certainly in an exercise model. I think fatigue is there to protect you from doing bad things to yourself, for the most part. And I'll entertain any questions you have.
Has anybody looked at finding inorganic phosphate to see whether that would improve?
I don't know of a way to sort of leach out inorganic phosphate. I'm not sure that there's something that would allow us to do that. Maybe there is, but I certainly have not seen any data on that. But that would obviously, if you had either a drug or some sort of nutritional supplement that would allow you to bind inorganic phosphate, that would allow you to look at that.
Does the use of anabolic steroids affect fatigue as far as
Well, put it this way. I'll ignore whatever psychological effects you have from this. But I don't think they're trivial in terms of how hard you might be willing to exercise. That said, increases in strength do increase your resistance to fatigue, in the sense that if let's say your max bench press is 100 pounds, which is probably about right. So we put 50 pounds on the bar and ask you to do how many reps can you do. And we just measure that. And then we put you on a strength training program, and now you can bench press 150 pounds. And we put you back at 50. You can do a lot more reps. So has your endurance gone up? Are you more resistant to fatigue? I would argue yes. What you also see is that your relative fatigue probably gets worse. That is, if now your max bench press is 150, if I put you at 75, which is your new 50%, you probably do fewer reps at the new 50 than you did prior to that. So if anabolic steroids facilitate you getting stronger, then yeah, I'd say your absolute endurance, in terms of these muscle tasks like this, not running or cycling, I would say that would probably be helpful. I guess I shouldn't say cycling, because certainly anabolic steroids, like the Tour de France, it's not just EPO, but testosterone. I think that's what Floyd Landis right? I mean, it was testosterone. It wasn't EPO. Now that said, fundamentally, when you exercise, you're trying to affect genes, right? You're trying to upregulate certain genes to increase protein synthesis. So when we typically think of anabolic steroids, you're typically thinking of contractile proteins. But when you engage in endurance exercise, you're trying to increase production of Krebs cycle enzymes, electron transport system enzymes, make more mitochondria, all that sort of stuff. That's protein synthesis. One can imagine that might be facilitated by higher levels of testosterone also. Yeah.
So what does the literature say about all these high-energy sports drinks and how they affect performance? Is it more gimmicks than reality, or is there some studies that actually prove that?
Well, there's a lot of research out there. A lot of it is funded by like the Gatorade Institute and stuff like that. But certainly the carbohydrate is potentially beneficial for certain types of exercise tasks. So now most people drink Gatorade, they're not spitting it out, right? But you drink a Gatorade beverage while you're doing some, Des Moines Marathon. We'll set up shop here at the Sports Med Club. When the Des Moines Marathon comes around, we got a water station. We'll have a Gatorade station. So carbohydrate hitting the mouth probably has some influence. Carbohydrate hitting the blood probably has some influence for that type of task. But if I'm doing how many reps can you do at 50% of your 1 rep max, probably not going to make any difference at all. So it really depends on the task. A lot of that, probably the fluid is maybe more important, certainly if you're exercising the heat and so on. But even the fluid, the fluid thing, after picking on Noakes, I'll give him props here. The whole hyponatremia business with marathon running, it was really Noakes who was pushing that for a long time, saying these people come into the tent after a marathon looking like they've got all the symptoms classically of dehydration, and they're not dehydrated. They've been drinking dilute water to an extent that's greater than they were losing in their sweat, and now they're in hyponatremia. And people were sticking IVs in them, thinking they were dehydrated, and potentially killing them in the tent after the race. So the fluid matters, but too much fluid is a problem also. So I don't know if I've answered your question or not, but when I teach statistics, I talk about interactions. It depends. Does Gatorade work or something like that? Well, it depends. I think for most exercise tasks, it probably doesn't make much difference. But tastes good. Yeah.
So I agree with your conclusions at the end, and obviously fatigue is a protective mechanism. There is no doubt in that. However, a couple of the data that you presented, it's surprising to me how easily the system can be fooled.
Yeah.
In the case of actually giving some sweet to the mouth kind of thing, and not getting necessarily the calories. And the other case, with the heat, simply hitting the head, again, the system is able to give more power.
Cooling the head.
No, I thought you had
They sat in the heat, but they had head cooling. But yeah. Although brain temperature is probably not a trivial factor here, right? I mean, the CNS is going to try and defend that pretty aggressively, too.
That mechanism can be very easily handled.
Manipulated? Yeah, let me give you another example. I saw this link last night on Facebook. So not all Facebook is wasting time, apparently, but Doug Coleman, who's Florida International, I guess, had posted this on the sports nutrition thing on Facebook, an article that came out in the New York Times. I haven't got the primary study yet, but what they were describing is a study, I think done in the UK, where they had people pedal against an avatar. And actually, our new system allows us to do that. So they had them do this over and over again. So the subjects knew what their capabilities were. And then they had them race against an avatar, and they were told that this avatar is basically at the level of performance that you're the mean over your last several trials or something like this. But they lied to them, and it was 2% higher. And the subjects were able to do that extra 2% if they believed they could do that extra 2%. Clearly the CNS is manipulatable under these conditions. There's been some other studies actually looking at Wingates, where you lie to them about how long the test is. A typical Wingate test lasts 30 seconds. So you manipulate the clock, so it actually goes 35 seconds or 40 seconds. Can they perform at a higher level if they think they're only 20 seconds in when they're really 25? That type of thing.
Where I was getting it was that some sensory information may be able to obviously overcome some others, affect higher priority, and where localized in the body this information is coming from.
Well, I'm not a psychologist, but I like to think of these things in terms of physiologic mechanisms. But certainly, the importance of the task influences your ability to tolerate unpleasant sensations, right? So that extra 2%, they're clearly capable of doing that extra 2% before. For whatever reason, they weren't. The CNS didn't have the right environment for that extra 2% to be expressed, but it could be. So what creates that environment? Some of it is you just want it more. What's that?
We also know that in the case of danger. When a danger...
Yeah. Well, I looked into that. You remember, you have all these anecdotal stories of the car falling on the kid and the grandmother picking the car up. Because Noakes referred to those when he's talking about central governor model. I cannot find them. These seem to be these urban legends. And if you look at these percent activation numbers, I mean, they're all like, they're mostly like, 90%. It was about as low as you see. So we can't, it's not easy to turn on everything. But we get close, even with just a normal subject off the street, no exercise training at all. Training can get you that, those last few percents of activation, but it's not like you're at 40% when you think you're working as hard as you can. You're in the 90s probably.
There was the recent evidence video report. It was a half dozen people lifting a car up off the motorcycle.
Yes. Yeah. But I bet 6 guys could lift it. That's.
Gals in there too.
There we go.
Well, anecdotally,
Yeah.
there used to be reports in player weightlifting where the coach would tell the athlete, it's 340 on the bar before 360.
Yeah.
Done 360.
Yeah.
But again, that's within the realm.
Yeah, but it's that's not.
Yeah, that's not.
Yeah, it's not like doubling your load or something like that. We have a reserve. I think it's clear that most people can't activate all the skeletal muscle if they're untrained. And even trained people can get pretty close to 100%, but how routinely they're able to do it is a different question. But it's not like we're down in the 40s or 50s. I mean, we're up there. Yeah.
So you showed the slide where you just put carbohydrate amounts and stood it out. Better. At what point in endurance exercise do you actually need to replenish your glycogen?
Well, while you're doing the task, you're not going to replenish glycogen. You're certainly going to be running. You're burning up glycogen from the liver and consuming glycogen in the active skeletal muscle. Directly answer your question, I don't know. Because it's not like we can put you in a scanner and say how many calories of carbohydrate you have stored. And because if we did, we could probably predict that point. But I don't know that we have a way to do that. Clearly, people do. I mean, they run out of carbohydrate, though. I mean, if they're used to. Yeah. But how fast you're going will influence how fast you're tapping into that, right? Yeah. So you could run a marathon and hardly tap into that at all if you went slow enough. Let me twist that a little bit. I think what straight percents of max, we use them because they're easy to think about, but without going into a whole lot of this physiology, we've got ventilatory thresholds, ventilatory threshold 1, ventilatory threshold 2. So how far you can go at a given pace or a given speed depends upon where that speed falls in these breakpoints. So sort of a standard way of expressing this is if you're at an intensity that's below ventilatory threshold 1, we would call that moderate intensity exercise, and you should be able to maintain that pace almost indefinitely. If you're between ventilatory threshold 1 and ventilatory threshold 2, depending upon where in that range you are, you could go anywhere upwards of an hour to maybe 20 minutes, depending upon how close you are to bumping those. If you're above ventilatory threshold 2, so somewhere between VT2 and max, it's in the single-digit minutes in terms of when you just couldn't maintain that pace anymore. And all of those would probably have nothing to do with carbohydrate, as long as you had adequate carbohydrate stores. So if you look at marathon running, which is, you pretty much have to start talking about 2-3 hour events before someone on a normal carbohydrate diet would really be at risk of running out of liver glycogen. The marathon speed seems to hover. People naturally gravitate towards speed that's right around VT1, maybe a little below, maybe a little above, depending on where they're at in the race. Under those conditions, normal carbohydrate diet, you shouldn't even 3 hours. You should be fine. Thank you.